We talked earlier in the course about how to handle massless pulleys. You may want to review that again before watching this video, because what I want to talk about here is how you handle pulleys when they have mass, and how that's different from how you handle them when they don't have mass. So I've got a problem here, going back to the old Atwood machine problem we did earlier in the course, which remember is 2 blocks with a rope slung over a pulley. Except in this case, instead of saying that the pulley is massless, the problem says that the pulley is 2 kilograms in mass, and it has to tell us, of course, the size and shape of the pulley. So it's a metal disc of radius 10 centimeters, a solid metal disc. So what is going to be the acceleration of the blocks now? So step 1. We need to do free body diagram here. Let's not worry about the details yet. Let's focus on going through the steps of the procedure. So we're going to have a total of 3 free body diagrams in this problem. 1 for the 10 kilogram block, 1 for the 5 kilogram block, and 1 for the pulley, which will be the new part. Let's do the blocks first, since this is just review. We're going to have gravitational force on both blocks, pointing downward, and we're going to have the tension force upwards on both blocks from that rope pulling up. So we'll have something like that. And then we also need a free body diagram for the pulley itself. Okay, now, what are the forces on the pulley? I don't know how kind of thorough and pedantic you want to be about this. Let's put in everything just to show you, even the ones that don't matter. First of all, there is rope going over the pulley, so we are going to need tension forces on the pulley from that rope. The rule is exactly the same as how you always do tension forces. You want to put these tension forces in the same direction that the rope is pointing at the location of the rope. So over here, we're going to have a tension force downwards like that. And over here, we're going to have a tension force downwards like that. My picture has gotten a little bit cluttered, but that's okay. So notice again that those 2 tension forces end up pointing straight down because they're coming straight down off the pulley. You would put them in whichever direction the rope is going when it comes off of the pulley, because that's the way the tension force is acting. And the magnitude of those tension forces, okay, let's say that this guy here is, let's say that this rope on the left is T1, and the rope on the right is T2. The tension force on the pulley is going to be the exact same value. It's just going to be opposite in direction. So basically the third law pair. Basically the third law pair on the tension force pulling the block up is the tension force pulling the pulley down. So we've got those 2 tension forces. If you want, you could also say, well, the pulley now has mass 2 kilograms, so there's a gravitational force on the pulley. How do I handle that? The short answer is it actually doesn't matter. The long answer is you put the gravitational force acting on the center of the pulley, which we'll cover in the next video, I think. But since this force is on the center of the pulley, it's actually not going to have any influence on how the pulley rotates. And if you want to be really thorough, you can say, well, wait a minute, there's 3 downward forces on the pulley, so why isn't the pulley dropping during this process? Well, that's because, of course, the pulley must be like hanging from the ceiling or something like that. It has to be anchored onto the ceiling. So if you want to, you could say, okay, there must be some little system here for keeping the pulley anchored onto the ceiling. Like maybe there's a little metal housing that's bolted into the ceiling like that. And that little metal housing is going to exert an upward force like that. So that'll be, I don't know what you want to call that. That's basically going to be some kind of support force. Let's say Fs, let's call it. Force of the support holding the pulley upwards. Okay. Now we've got some free body diagrams to work with. Now let's start thinking about F equals ma equations. So we're going to have one F equals ma equation for the left-hand block because it's one-dimensional, one F equals ma equation for the right-hand block, and then for the pulley, we're going to need to use torques and have a torque equation. So let's do this one step at a time. For the 10 kilogram block, we're going to have T1 points upwards. We're going to have its weight points downwards. So I'm going to drop the units here and just make this 10g. And I should be careful about my acceleration. I'm going to assume the 10 kilogram block drops down and the 5 kilogram block rises up because the 10 kilogram block is heavier. So that would mean this should be minus 10a because the acceleration is downwards. For the 5 kilogram block, I'm going to have T2 minus 5g equals positive 5a. So those are just F equals ma equations. Now, how do we handle the pulley? That's the real question. How do we handle the pulley? So first of all, we've got our free body diagram. That's step one. Step two, we need to identify where is the axis of rotation about which this pulley is rotating. And that's going to be the center of the pulley there, marked with an X. One thing you'll notice right away is that since I marked the gravitational force and the support force as both acting at that location, those two forces are not going to exert any torque. So there's only going to be two torques acting on the pulley. And those two torques are going to be coming from T1 and T2. So what I want to do here is have a tau equals I alpha equation for the pulley. So first the torques. We're going to have torque number 1 is equal to, first of all, tension number 1 is causing a counterclockwise rotation of the pulley. So this will be positive. Second of all, I want to use FTL to generate this torque. So this is, I'm using FTL. So FT is just going to be T1 because you'll notice this force is already tangent to the circle, tangent to the pulley. And the value of L is going to be here. That would be L. And that's just the radius of the pulley. So it's going to be T1 times the radius of the pulley, which is 10 centimeters or 0.1 meters. Next up, T2. So torque 2 is going to be by exactly the same argument. It's a clockwise torque, so it's negative. The force is T2, and the L value is still the radius of the pulley again. So we'll have something like that. We're also going to need a moment of inertia for the pulley. It's a solid disc. So you look up the moment of inertia for a solid disc. A disc is basically just a short cylinder. So it's really a solid cylinder. So that would be 1/2 mr square is the formula for the cylinder. That's coming from the table of moments of inertia. The mass is 2. The radius is 0.1. So that's going to be, oh, I can do that one in my head. 1/2 of 2 is 1. 0.1 square is 0.01. And then lastly, how are we going to deal with alpha? Because I don't really want to introduce a new variable into this problem with alpha. But here's the thing, alpha is related to A because as the pulley rotates, the block is going to drop by the same amount that the pulley rotates. So as a result, we're going to have A equals alpha times R, which will be 0.1 times alpha. So A is 0.1 times alpha. Okay, so if I collect all this information and put it all back into the tau equals I alpha equation, I'm going to end up with 0.1 T1 minus 0.1 T2 equals 0.01. That's the moment of inertia. And then I want to get rid of alpha and turn it into an A. So I'm going to put here A over 0.1. okay? And then, believe it or not, you can actually divide this whole equation by 0.1, and it'll cancel out this and this and this and this, and get rid of all of the numerical factors in this particular case. So we're going to end up with just simply T1 minus T2 equals A. And that's the equation which gives you the physics of the pulley itself. One thing I want to draw attention to is that you'll notice T1 does not equal T2 in this case. In the old days with a massless pulley, we would assume T1 equals T2. But here you can see clearly T1 does not equal T2 because T1 minus T2 is not equal to 0. So giving the pulley mass means that we also have tension forces which are not equal to each other. Okay, so now we've now got 1, 2, 3 equations for 3 unknowns, T1, T2, A. So we have 3 variables and 3 equations. So this is solvable. I'm going to need to make a little bit of space. I'm not going to try to squeeze this into the little teeny amount of space I have left. Let's get rid of all this background work. Okay. So start solving. So let's say that I'll solve equation 1 for T1. That's pretty easy. So T1 equals 10G minus 10A. Let's solve equation 2 for T2. T2 equals 5G plus 5A. And we'll substitute everything in over here and that'll give me 10G minus 10A minus the quantity 5G plus 5A equals A. So that's going to give me 10G minus 5G is 5G. And then I'll have minus 10A minus 5A is minus 15A equals A. Move the A's to the other side. We'll get 5G equals 16A. And that'll give me A equals 5 times 9.8 over 16 is 3.06. And I got a positive answer, which means I was correct about the direction that everything is rotating. The 10 kilogram block is accelerating down. The pulley, by the way, I assumed in this solution here that the pulley was accelerating counterclockwise because I made this positive here. So that was equivalent to assuming that alpha was positive, which means the pulley rotates counterclockwise. And the pulley, the block on the right goes up. So that notice that they're all moving together. The block on the left is going down, the pulley is rotating this way, and the block on the right is going up. So that's all consistent with each other. I got a positive A, which means all 3 of those are correct, and that is in fact the way the system is going to accelerate.